Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Mia de los Reyes with us today. Hey, Mia.
Hello. It's great to be here. Thanks so much for having me.
Thank you so much for talking about your very lovely article. It's fantastic. You win the prize for being the first person to do one of these outside.
Right.
You have a GoPro? Is that what you're working off of, or are you working off your laptop?
I'm working off my laptop right now. The weather is just too nice to be inside right now.
Cool. Where are you at?
So I'm in Pasadena, California, although I'm moving soon.
Cool. I was there. It is June 27th of 2022, a little after solstice as we shoot this. And I was in Pasadena last week with 1,500 of my colleagues and your colleagues. We were at AAS 240 in Pasadena. So yeah, it was very lovely in Pasadena this past week. Very cool.
Yeah, there was a bit of a heat wave during AAS, and it seems to have calmed down at least a little bit since then, which is unfortunate for everyone who came into town and had to experience the heat for that 1 week.
I'm in Phoenix, and so I considered it like a vacation period. It was like, this is so great. It's only 95.
That's for sure.
What are people complaining about? Oh, very cool. Very cool. And Mia, what's your institutional affiliation these days?
So I have just graduated from Caltech, actually. So I guess it's Dr. Mia.
It's Dr. Mia. It's Dr. Mia. That is awesome. Very cool.
So I'm moving soon to Stanford, so I'll be there for a year. And then after that, I'm starting a position at Amherst College in Massachusetts.
Oh, very nice. Very nice. Awesome. Congratulations on all that. That is wonderful news.
Thank you. I'm really excited.
Cool. And Mia, what do you like to do for research?
So I'm an observer. I study mostly dwarf galaxies, so low mass galaxies, roughly 10 to 100 times less massive than Milky Way sized galaxies.
Okay.
And my main goal is really trying to understand where we come from, so very broadly, and that takes two forms. One is, where do the constituent particles that make us up come from? So where do the elements of the periodic table come from? And to do that, I study a whole subfield called galactic archaeology.
Mm-hmm.
But then the other sort of direction that I like to approach this question is on a much larger scale. Where did our Milky Way come from? Where did our home come from? And to understand how galaxies like the Milky Way form and evolve, it's really important to understand how low mass galaxies, which we think are the building blocks for these more massive galaxies, come from.
Cool.
That was a very long-winded answer, but
No,
I really like
fantastic.
galaxies. I like low mass galaxies. And I like studying them in all kinds of ways.
And baryons, we like periodic tables. Very
Yeah.
cool. And that is going to bring us to this awesome AJ article, or APJ article. It's open access, people. You can get it for free. Go get it. Simultaneous constraints on the star formation history and nucleosynthesis of Sculptor or spheroidal dSph. And Mia, take us away.
Sure. So this is work that I've done with my advisor, or he's always my advisor, Evan Kirby.
They never go away, really.
Right. They're there for life. So he's affiliated with Caltech, and he's moving to Notre Dame. And then we also have co-authors Alex G. and Evan Nunez, so both of whom were really excellent. Everyone on this project was really great to work with, and I really enjoy having co-authors that I really like and respect as people and scientists.
Cool.
So the overall idea of this project was to measure the star formation history of galaxies. So this is a major question in understanding how galaxies form and evolve. It's sort of the underlying thing driving star formation overall, is the overall thing that's driving how galaxies evolve. And so understanding that process over time, the star formation rate as a function of time, what we call the star formation history, is really key. And so this is not a new idea, and people have developed a lot of different ways to do this. One of the most common is using color magnitude diagrams. So the idea is you measure the colors and magnitudes of resolved stars in nearby galaxies, or in the Milky Way itself. And we plot all of those stars on a colored magnitude diagram and then try to fit them with model isochrones.
Okay.
So this works fairly well for measuring the absolute ages of stars, but it struggles, especially when we look at very old and metal poor stellar populations.
Yeah.
So we get this, what's called the age metallicity degeneracy, where particularly when we go to old ages and metal poor populations, the isochrones become sort of degenerate between age and metallicity. It's hard to tell the difference. And even if you keep every single parameter the same and change something like age, for example, an isochrone at 11 gigayears compared to 13 gig years age, will have a really tiny difference in magnitude.
Mm.
And much smaller than is actually used, much smaller than I would say the discrepancy between model sets of isochrones. So depending on which models you use, you can get really different answers.
Okay.
So to get around that, rather than using photometry, so this is really a photometric method, you're using colors and magnitudes, we'd like to use spectroscopy.
Ooh, cool.
So I like to compare this to bananas.
Okay.
If you look at relatively young bananas, it's usually pretty easy to tell the difference between a banana that's fresh, that's totally like not ripe yet, and a banana that's been ripe for maybe 1 or 2 days. But if you start looking at bananas that have been, over ripened, bananas that are weeks old, it becomes really hard to tell the difference between a banana that's 9 weeks old and a banana that's 10 weeks old. Looking at the color is not enough. But if you could measure the chemical composition of the banana, that would help a lot. And so it's the exact same thing. The idea is instead of using photometry to measure colors, we're going to use spectroscopy to measure chemical abundances in stars.
Cool. Yep. Very
And
nice.
this is really helpful for measuring times in the history of a galaxy, because as we see in figure 1, different nucleosynthetic events, different events that make elements, occur at different times in a galaxy's history. So if we have a single burst of star formation history at time t equals 0, then at some delay time after that, we start to see these nucleosynthetic events. So that's what this is really showing. It's just the number of these events that occur as a function of delay time.
Mm-hmm.
So for core collapse supernovae, they're the most massive stars. So after a burst of star formation, they're the most likely, the fastest to occur. And so that's this solid line here.
Mm-hmm.
At some point after that, we see intermediate mass stars become asymptotic giant branch or AGB stars. And they begin to produce these stellar winds that also produce elements. And that happens because they're intermediate mass stars that live longer. That happens sometime after core collapse supernovae.
Right. Good.
And then latest of all, we see these very low mass stars that occasionally explode as type 1a supernovae. And so that's this dotted line here.
Okay.
And then because these different nucleosynthetic events produce different elements, they have specific elements that they're more likely to produce, as shown in figure 2, we can actually trace the overall time in a galaxy's history by looking at sort of the concentrations of different elements. So for example, magnesium, which is the second panel in figure 2, is what we call an alpha element, which are predominantly produced by core collapse supernovae. So you can see the solid line at the start, at the early delay times, is really high compared to the other two lines.
Okay.
Look at, for example, iron group elements like manganese and iron, so slightly lower. We see that the dotted line for type 1a supernovae, the iron group elements are mostly made by type 1a supernovae. And so this dotted line for type 1a supernovae also becomes very high.
Okay.
So by tracing the overall concentration of ratios of these elements or different combinations of these elements, we can deduce something about what happened in the galaxy's past.
Cool.
That's the overall premise of what we're doing today, using something called a galactic chemical evolution model, or GCE model, which again, none of this is really new. I think Beatrice Tinsley in the late 70s was really the first person to propose how to do this. So since the 70s, it's been some time. We've had some time to try to figure out how to do this. And people have, come up with increasingly more complicated GCE models over time. We're going to use a relatively simple one. The thing that we're doing that's new in comparison to sort of previous GCE models is that we're putting in a lot of elements. So typically GCE models trace alpha elements like magnesium and maybe iron, maybe 1 or 2 other iron peak elements.
Yes.
But we're including a lot of alpha elements, so not just magnesium, but several other alpha elements, iron and a few other iron group elements. And we're also including what we're terming S process elements. So these are the elements that are mostly made by AGB stars, or at least some component of them is made by AGB stars. So these are these intermediate mass stars. So this is really helpful because it lets us probe not just the extreme ends, extreme times, not just the earliest times and the latest times in a galaxy's history, but it also lets us get a handle on what's happening in between in this intermediate time range.
I'm with you.
So that's the overall plan.
Cool.
The other thing that we'd like to do is, measure both the star formation history, but also see if this will tell us anything about how these elements are produced. So there are a lot of open questions in understanding the nucleosynthesis of elements. So one of them, for example, is the role of the R process, the rapid neutron capture process. So that's something we'll get to in a bit.
Okay.
But our hope is that our GC model will not only be able to tell us about the star formation history, but also these other things. So really quickly, I'll touch on our process. It's probably the most uncertain of the nucleosynthetic processes. So only recently have we realized that quite a lot of our process elements likely come from neutron star mergers. That was confirmed with some of the earliest measurements of a neutron star merger from LIGO.
Okay.
And so to start, we're going to just completely ignore the R process. And we'll do that by using europium, which is a known R process element, and that it's almost entirely produced by the R process, to sort of subtract out the R process contribution from our other elements. So in particular, barium is a little questionable because barium is produced by both the S process in AGB winds and by R process events. So we're sort of here, we're fitting a line. The exact details you can read about them in the paper, but the idea is to sort of initially remove the R process contribution and just try to fit the S process.
Okay.
All right, and then the overall chemical evolution model that we're working with is shown in, I think, equation 3. It's just on the right there. Yeah, equation 3, great. So the idea is that we're tracing the overall contribution to the gas phase metallicity from a bunch of different things. So first of all, star formation turns heavy elements that are in the gas into heavy elements that are locked in stars. So that takes away from the gas phase abundance.
That's the minus sign.
Yeah, hence the minus sign. We have a lot of plus signs from what are marked as 2, 1A, and AGB. Those are the nucleosynthetic events that we're considering. So core collapse supernovae, AGB stars, and type 1A supernovae. And then our galaxy will also have, it's not a closed box. No galaxy is a closed box. So there are inflows and outflows of gas that are both adding elements, mostly pristine gas, so not really much in the way of heavy elements, but they're also removing gas. And so we have to make assumptions about all of these things in order to put together a whole chemical evolution model. So to trace star formation, we use something called the Kennigan-Schmidt law, or the global star formation law, which is essentially just a power law because we're astronomers and we like power laws. And also because in most environments, it seems that there's a sort of a power law relationship between the amount of gas and the amount of star formation in a galaxy. For the 3 contributions from nucleosynthetic yields, we use a parameterized set of stellar yields, which I will get to, well, maybe we'll save that for the very end when we talk about the appendix.
Okay.
But the idea is we have to parameterize yields from the 3 sources I talked about. So core collapse supernovae, AGB stars, and type 1A supernovae. And I think, yeah, that's at the very bottom. And then we also have the inflow and outflow contributions. And so those are in some ways the largest assumptions that we're making going into the model. The outflow assumption is just that the outflows are proportional to the number of supernovae, which is probably reasonable for dwarf galaxies. So Sculptor, which is the sort of test case that we use, doesn't appear to have an AGN, an active galactic nucleus or anything. So it's likely that the outflows really are predominantly caused by supernovae. So this is not an unreasonable assumption. The main assumption is the inflow, shown in equation 5. So we have sort of picked a parameterization that we know works for Sculptor because several other people have done studies showing that this is actually a decent functional form for a galaxy like Sculptor. But this is sort of the limiting factor of our chemical evolution model. It's what we call a one-zone model. Really only making assumptions about, like, it's assuming that the entire galaxy is well mixed and that there's sort of one chemical evolution zone. And this is fine for Sculptor in particular because it is a nice and well-behaved, in many ways, dwarf galaxy. But if we start looking at other dwarf galaxies in the local group, this assumption becomes a lot more questionable. The star formation, the gas inflow rate is not necessarily as simple, and the overall star formation history is not as simple.
Fair enough.
This is sort of a major caveat, I think, about our study.
Okay, good.
The goal is that we put all these things together along with other information. So if we scroll down to what are we on now? Figure 4?
We are on, there's a catalog of some of our
Yeah, the catalog of the stars showing the abundances in case anyone wants to try to reproduce this.
Absolutely, very good. Figure 4 is the lifetimes of your stars.
Right. So figure 4 is another input that we have to put in is the overall lifetime of the star. And this is just because that tells us when, so, you know, if we have a burst of star formation history, when do we need to add the chemical elements produced by core collapse supernovae or AGB stars, things that happen at the end of a star's lifetime.
Mm-hmm.
So we put all of this in. The nice thing is that the overall, as you can see here, the very rough model that previous GCE models have sort of relied on, so this is an analytic model, matches pretty well with the numerical result from stellar population codes like BPAS.
Ah, right. Uh-huh.
Yeah, so that's the overall goal of this. It's just to show that, you know, we're not just pulling this equation out of nowhere.
There.
Right. But then the major results, I think, are shown in figure 5. So the results of this GCE model.
Okay, lifetime.
So we'll see how, I think it's figure 5 anyway.
Some of the input, and there we go. This is, yes, there we go.
Yeah, so this entire section is just about fitting the chemical evolution model. And here we go. Here's what actually happens when we try to do that for a galaxy like Sculptor. So in the top panel, we're showing the metallicity distribution function from 2 different, so our data come from 2 different sources, both the DART team, which use VLT, and DEMOS on Keck.
Okay.
So they're slightly different. DART has higher resolution spectroscopy. DEMOS has medium resolution spectroscopy. So there's likely some systematic selection effects in both samples. So we try to fit both simultaneously.
That's the black curve?
Yeah, that's the black curve.
Okay.
So the black is our model fit, and the blue and orange are the data points.
Okay.
So as we can see here, our black model does a pretty good job of fitting all of these chemical abundances. So if you scroll down a little bit, you can see the black line goes through the colored points, which is really,
and then we got
that's the main
magnesium.
thing we were trying to get to. So we have magnesium, silicon, and calcium, which are alpha elements.
Yeah, there's an alpha signature right there.
Yeah.
Calcium, also alpha, and
Yep.
barium.
And then barium is really the interesting one that people have not typically tried to put in these chemical evolution models.
Fair enough.
So again, these are, we removed sort of the R process contribution. So this is nominally just the S process contribution to barium. And our line goes through the colored points. So that overall seems like a good fit. And then on the right in figure 6, we can see sort of the outputs from this model. So you can actually trace the overall growth of a galaxy in terms of gas mass and stellar mass. You can see the inflows and outflows in the different mass components, the overall metallicity as a function of time. And then in the last panel, the rate of these nucleosynthetic events as a function of time.
Okay.
So this is what our best fit model tells us.
Okay.
And the final mass of the galaxy that we get from this model is about 1.2 times 10 to the 6 solar masses, which is exactly what we expect for Sculptor from independent mass measurements. So everything looks good so far.
Yep, very good.
And then in figure 7, we can see what that tells us about the star formation history of Sculptor. So here we're looking at the cumulative star formation history as a function of look back time, which the units are, every time I think about this, the units are kind of wonky. I have to always subtract, 13 point whatever in my head.
Yes.
But as we can see here, so the dashed lines, the colored dashed lines, these are all the star formation histories measured from color magnitude diagrams.
Okay.
So the purple and the pink and the green. In particular, the green is sort of one of the more recent measurements from Dan Wise's group. So Dan Wise has measured, so these is sort of the deepest photometry that we have from Hubble. And so we can see that there are quite large error bars, especially as you go further back in time. When you start looking at look back times greater than 10, the error bars become quite huge if you're looking at the the x-axis error bars. And so our work and the other spectroscopic measurements are shown as dotted lines.
Okay.
So in particular, the teal line from Evan Kirby's work from 2011 is sort of the most similar to what we've done in this paper. We've just added a lot more elements and more data. Okay. And so it's not a huge surprise that our work matches Evan's work fairly well. They're very similar models. What is a little surprising is that there's such a big discrepancy between the spectroscopic measurements, the dotted lines, and the photometric measurements, the dashed lines.
Right.
So some of these dashed lines, they say that Sculptor hasn't finished forming its stars until, 6 to 8 gigayears after it starts forming, which is a huge amount of time. Our model predicts that Sculptor finished all of its star formation within about a gigayear.
Yeah.
So there's a huge difference there. And actually, I think this is something that I think is really important. We need to find some way to reconcile the photometric measurements and the spectroscopic measurements. So this is something I think a lot of people are aware of. And it's not clear exactly what the path forward is.
Right.
But hopefully we've shown that, just adding more elements doesn't help solve this discrepancy.
The tension remains.
Yeah, there are some indications that it's not totally horrible. So if we look at the first 80% of star formation history, so from 0 to 0.8, and we compare like our models with, for example, the error bars on Dan Wise's models, you could see how those are roughly consistent until it's really just the last, 10 to 20% of star formation that we're not sure about.
Okay, fair enough.
The other caveat I want to point out is that all of the spectroscopic measurements, spectroscopy is great for telling us relative ages when we look at old populations. It's great for breaking that age metallicity degeneracy. But it's not great at giving us absolute ages. And so the overall position on the x-axis of all of the dotted lines and the black line from our model is not actually that certain. So we can make assumptions about where it should be, but you need to imagine sort of shifting those lines left and right.
Right.
Yeah. So it's a complicated problem. I think there's still a lot to be done in this area, but it does show that spectroscopy alone can put useful constraints on star formation history.
Cool. Very good.
All right. So more than just the star formation history. Oh, I guess really quickly, let's talk a little bit about the model, the assumptions that we make in this model.
Okay.
We make a lot of assumptions, as I've discussed. So if we scroll down a bit to figure 8. Yeah, here we go.
Yes, yeah.
Right. So as I mentioned, the biggest assumption that we're making about in our model, or what I feel is the biggest assumption, is the assumption of gas inflow. Because that's the thing that really shapes the overall star formation history of a galaxy, right? If you put in gas, you're going to make stars. And so the rate at which you put in gas is going to change the overall star formation history. So we tested a bunch of different a bunch of different gas inflow parameterizations to see what that would do to our model. And as we can see here, we tested what happens if you just put in a constant inflow, what happens if you put in exponentially declining gas inflow, this dotted line. And we can see they don't do a great job of fitting the overall metallicity distribution function of the galaxy. So this suggests that our assumption of the gas inflow is probably okay. Again, for Sculptor, this is probably a decent assumption.
All right. Remind me what AIC stands for.
So AIC stands for, I'm going to pronounce this horribly. I just know it. It stands for the Akaike Information Criterion. So it's just sort of a Bayesian criterion that tells us about goodness of fit.
Got it. Okay.
So a really high delta AIC means because AIC is sort of a relative comparison, the actual number itself doesn't mean anything. You just use it to compare models.
Yeah, high and low.
So a very large positive number means it's a worse fit to our data than the black line. So obviously the purple is a terrible fit to our data. So the delta AIC is very high.
Okay.
The pink is only a slightly worse fit to the data than our black line, but it is still not a great fit to our data.
Yeah,
that's overall.
A little long, extra little bump here. Yeah.
Yeah. So that's so we'll keep using this delta AIC nomenclature. So thank you for the reminder to explain it.
Well, I figured it was not accretion-induced collapse. So I had to ask.
That's fair. So if we go to the next panel, we'll see what else we can test. So this delta AIC. So all right, so here we're changing a lot of things in the model to see what happens and to the star formation history, and to see if we don't show the fits with the metallicity distribution function or anything, but we do explain the delta AIC. So in the first panel, we are testing a couple of different things. So not only are we testing the effect of, for example, ram pressure stripping. So Sculptor is a dwarf galaxy. around the Milky Way.
Yeah.
Milky Way has, there are tidal effects. There's the ram pressure stripping effect of just any galaxy that comes into relatively hot halo will get stripped of its gas. And so we do a couple of tests based on when we think ram pressure might have begun occurring in Sculptor to see what happens. And as you can see here, it doesn't really do much to the overall star formation history.
Right.
Yeah, the orange dotted line is basically equivalent to the black line, and the delta AIC is 0. So
yeah, because usually it's the material out there is hot and tenuous, and it's not going to form stars anyway.
Right, exactly.
Yeah.
But also removing gas from the galaxy doesn't appear in this particular way. It doesn't appear to do anything.
Okay.
Let's see.
Cool.
So as a point of comparison, we also show this teal dotted dash line. That's the model that we just talked about. What happens if we put in a different gas inflow parameterization?
Okay.
And we see that again, as we saw before, it wasn't the best fit to our metallicity distribution function, but this is mostly to demonstrate what happens to the star formation history.
Right.
And it actually makes it shorter.
Shorter, not
even shorter than our already quite short measurement.
Mm.
We can also test things like changing the IMF. So that's what we're doing in the bottom panel. So the IMF can have the effect of extending the star formation history.
Yes.
And the delta AIC can also, depending on which IMF you're looking at, it might actually do a better job. The salpeter IMF in particular might do a better job of fitting our data than the fiducia model.
Okay.
So this is really a test to see if we push the limits of our model, if we push the assumptions or tweak the assumptions, what is the maximum amount that it would change the star formation history?
Yep.
And so we see here that it does change the star formation history if we change the IMF, but by a relatively small factor. So we go from 1 gigayear to maybe 1.25 gigayears, which is really different from it's still very different from the 6 to 8 gigayears that photometric measurements might suggest. All right, and then finally, the last thing. So other than the gas inflow model definitely affects the overall shape of the star formation history. But by far, other than that, the largest assumption that we're making, or the biggest leap that we're making, is with the type 1a delay time distribution, which is really not well known. So yikes. I think to some extent, we know that it is probably close to a t to the -1 power law. This was actually a little sidebar. This was actually the whole purpose of this. This is why we started this project, is because we were trying to come up with a way to measure the type 1a delay time distribution. And we ended up going down this giant rabbit hole of just chemically modeling Sculptor to begin with. So we're hoping in the future in the near future to have another paper sort of diving in more detail on just the type 1a delay time distribution. Because it depends a lot on the physics of type 1a supernovae, which may vary depending on the environment. It's also not well known, I don't think, in any environment. So that's something we're hoping to work towards.
Very nice.
But for now, we can see that just changing the delay time distribution by quite a lot. So I think some of these modifications are quite unreasonable. For instance, changing the minimum delay time for a type 1a supernova, so that the minimum time it takes for a type 1a supernova after a burst of star formation. 50 megayears is, I think, quite a short amount of time compared to a lot of supernova models and stellar population synthesis models, or rather, for the most part, binary population synthesis models. Right. And we can see that even changing the delay time distribution by quite a lot, although it looks like the overall sort of star formation history gets stretched or compressed, it's still not by a lot. No. So again, we can't come anywhere close to the 6 gigayear star formation timescales that some photometric models might predict. Right. So again, we're hoping to focus in more on what this can tell us about type 1a supernovae in particular. Yay. But that'll have to wait for a future paper. In the meantime, if we scroll a bit down, so here we're sort of just testing a bunch of different models. But again, one of the other goals of our paper was not just to measure the star formation history, but to also discuss sort of other questions about nucleosynthesis and see if our model could tell us anything about those.
Okay.
So we've just spent a lot of time talking about the type 1a delay time distribution, but type 1a supernovae are also interesting in that nucleosynthesis alone can tell us something about the physical channel that produces type 1a supernovae.
Okay.
So for example, when we look at elements like manganese and nickel, these are iron group elements,
Yes.
and they actually show a quite strong dependence on the overall mass of a type 1a supernova, of the white dwarf that explodes as a type 1a supernova. So that's shown here by these colored tracks. So the black and the purple tracks at the top, those are near Chandrasekhar mass models. So models that explode close to the 1.4 solar mass regime. The sub-Chandrasekhar mass models are these lighter colors, the pink and orange, yellow. I picked this color scheme and I don't really know what color.
I call it orangey, but okay.
Yeah, orange. Yeah. So if you look at those two, they typically produce much less nickel and manganese than the near Chandrasekhar mass models. So just by looking at the amount of manganese and nickel, manganese in particular, I had written an entire previous paper about this.
Yes.
I'm a fanganese of manganese. So
very cool.
It's a pretty good indicator of the overall mass of type 1a supernovae. And so this is sort of corroborating what we had measured earlier just by looking at manganese in this previous paper. We see that it's these sub-Chandrasekhar mass models that do a much better job of matching the manganese and nickel abundances in Sculptor.
Good, yes.
All right, so this is type 1a supernovae.
Interesting.
The other sort of, I think one of the other major nucleosynthetic events that is extremely uncertain, as we've discussed, are neutron star mergers. So neutron star mergers also have a delay time distribution that is dependent on the overall physics of where they occur. So if we scroll down to figure 11, so this is a little more complicated in order, I think, to explain. But the idea is that we're trying to test different prompt or delayed channels. So we're effectively, again, changing the delay time distribution of neutron star mergers and trying to see if we can match both the barium abundances and the europium abundances.
Okay.
We don't use, like I said, we don't use our process in our original chemical evolution model, mostly because we wanted to try adding it on top of sort of the fiducial model, the best fit model.
Fair enough.
To see if we could get it to match these elements, if that makes sense.
Yep, makes sense.
Right. So the idea is if we look on the left, so I should say almost all of the fits that we do, all of the model lines in this plot are uncertain in some way, in the sense that we don't know actually what we're even less certain about the neutron star merger delay time distribution than we are the type 1a delay time distribution. And we also are the yields, the exact amount of elements produced by each neutron star merger is also very uncertain, and also probably it's stochastic in some way. There's no guarantee that every single neutron star merger makes the same amount of elements.
Fair enough, yes.
So everything is kind of uncertain, but we use sort of our best guess from the literature in the left panels.
Okay.
We sort of assume two major R process channels. So the prompt channel, we assume are not from neutron star mergers. We assume they're from core collapse supernovae of some kind. And so that's this sort of darker blue color. There we go. Yeah.
Darker blue. Yep.
Right. And so we can see that adding this prompt channel increases the amount of R process elements at relatively early times.
Yes.
Or relatively low metallicities early times.
Yes.
So compared to the light line, which has no R process at all.
The green. Yes. Okay.
Yeah. The cyan green. Yeah. There's some slight increase. If we add a delayed R-Pros event, so this is something closer to a neutron star merger, since it takes some delay for neutron stars to form and then merge. That's this purple line here. That does a better job. So it increases the amount of R process elements, and it does a better job of reaching these data points. But it's, as you can see, especially in the bottom panel, the purple line doesn't really go through most of those points.
Right. So purple and black here are a little overlaid.
Yeah. So the black is combined, prompt and delayed.
Okay, so they're essentially the same. Okay, got
Yeah,
it.
basically the delayed time is the delayed contribution is really contributing most of the elements here.
I'm with
All
you.
right, so
Still low.
sorry.
Still low relative to the
Yes,
observations.
exactly.
Right.
So
Hmm.
clearly these assumptions that we've put about the delayed time distribution and about the yields are not right. Something is not right. Either we need more nucleosynthetic events, or we need much higher yields. And so on the right side, we basically just try to dial a bunch of knobs to see what it requires to get these lines to match the data.
Okay.
So we try hugely increasing the amount of our process elements from prompt prompt model. So that's this dashed blue line. And we try combining that with the delayed yield. So here we can see that does a much better job of pushing up the overall abundances that we're looking at.
Yep.
We try adding that to a delayed yield. We try increasing the delayed yield by quite a lot. So, you know, multiplying the number of neutron star mergers by 5.
Right.
Is probably unrealistic, but this is sort of what's required, it seems, to actually get it to match.
Wow. Wow.
Yeah, and so in total, we find that, you know, definitely the models, the assumptions that we're making about neutron star mergers and potential core collapse supernova contributions to the R process, there's something that we're missing.
Something's got to give.
Yeah. And also it seems that we need a combination of both, really. You need both the prompt and delayed channels. So this is more or less consistent with what other people have measured from similar chemical evolution models, both in dwarf galaxies and in the Milky Way, is that it is likely that there's some contribution from multiple models, from multiple channels, I should say. It's not clear which is the dominant channel. I think that's going to be a big question. I think most people are leaning towards delayed neutron star mergers, but I think it's still unsettled, and it will be really interesting to see, to see what folks come up with, and also to see if we can change or if we can better our understanding of the delay time distribution of these things.
Indeed.
Or the yields. I mean, having better yields would help by a lot. Just better estimate. Yeah. Right now, a lot of these are, I think, quite order of magnitude estimations.
Fair enough. Yep.
Yeah. So this is the last figure in the paper. I do want to quickly scroll down to the appendix just to show. We include, you know, all of the priors and parameters and best fit.
Here we go.
Best fit values for the parameters in case anyone wants to reproduce them. And then importantly, we include our yield parameterizations for the nucleosynthetic yields. So this is another thing that our model does a little differently from other models. Most models will pick, so there are, you know, various yields out there.
Yes, there are.
So a number of different models for type 1a supernovae, for example, that have their own yield tables. And typically, previous chemical evolution models have picked one and then just said, okay, we're going to use this for the rest of our model.
Fair enough.
We sort of do that. So we actually went through and tried to determine, for example, in figure 12, these are from type 1a supernova models. We tried to see what would happen if we tweaked any of these parameters. So we tried sort of the full range of parameters of yields. So for instance, for carbon, the top line, we tried seeing what if changing the amount of carbon from either this sort of first yield, which is very close to 0 for most models, and then this one pure deflagration Chandrasekhar model by Xingqi Leng has a much higher carbon yield. So we tried that too. And it did significantly affect the overall trend of carbon. So we decided to just pick a number and be done, right? There were some elements, however, so iron shown, which is highlighted in blue text.
Yes.
It turned out actually changing the amount of iron produced by type 1a supernovae did have a large effect. So we actually allowed it to vary as a parameter in our model.
Got it.
And so that led us to this best fit yield shown in the teal dashed line there. And we did the same for both the core collapse and the AGB yields as well.
Okay.
So for type 1a supernovae, it's a little simpler because as far as we know, there's no compelling evidence that the mass of the white dwarf, other than for some elements like manganese and nickel, there's no evidence that the mass of the white dwarf necessarily has a huge impact on the yield.
Okay.
On the yield of heavy elements, rather. But there's a very strong correlation that people have modeled very well for core collapse supernovae and for AGB stars. So there are very strong trends as a function of stellar mass of the progenitor star. And so we actually sort of qualitatively parameterize different sets of models. So we look at, for example, Ken Nemoto's models from 2013. Those are all the solid lines.
Yep.
And the Lamongi and Chief yields from 2018 as the dotted lines. And again, all of the elements that are highlighted in blue, those are the ones that seem to have the biggest impact on overall elemental trends. And so those are actually free parameters. So all of the other ones we sort of just, in many cases, there was no significant difference between the two models. So we just picked sort of a parameterization that looked close to both of them. But for calcium, magnesium, and carbon, we actually let this overall trend vary.
Okay.
As a function of both mass and metallicity. And the same for AGB stars. So all of those parameterizations, I think this might be helpful for modelers in particular, for people who, you know, are running models like fire, for example, feedback in realistic environments. If you're trying to model nucleosynthesis in dwarf galaxies, we have a whole table that's on the next page of all of the equations, the exact equations that we used to parameterize these yields, including the best fit yields.
Very nice.
So our hope is that, you know, this can be useful for people in if experimenting with chemical evolution models, experimenting with, I guess there's still chemical evolution models like fire, hydrodynamic models, who want to, you know, post-process and put in chemical yields later. So hopefully this will be a good resource for those folks. And I think, hopefully this is a useful thing for folks to know, that
it is.
Understanding chemical evolution can tell us about star formation histories. And there's definitely still some work to do in the field.
Absolutely. So very cool. Yeah, thank you so much for walking us through your very lovely APJ article. And you touched on a little bit twice as we walk through the paper, and then a little bit there at the end. And so where do you think we go, let's say, over the next 2 to 5 years on this topic? Are there new telescopes coming online that will be able to take suitable spectra that can detect one? Are there additional theoretical models that can be done? We can always cross our fingers for another neutron star merger or type 1a supernovae in our galaxy. We can hope for those. But just kind of where do we go without being so serendipitously lucky over the next couple of years?
No, that's a good question. I mean, so as I said, our model, I think the model itself has some limitations. So one of them is the requirement for a relatively simple star formation history. And if you look at anything more complicated than a dwarf galaxy, for instance, the Milky Way, you could never hope to model the Milky Way in a one-zone chemical evolution model. It's just too complicated. There are too many moving parts. It has a complicated accretion history, etc. But there is a population of galaxies where the observations are relatively limited, but I think would be a really good fit for models like these. And those are ultra faint dwarf galaxies.
Oh, yeah.
So they're even smaller than Sculptor. They definitely have really simple star formation histories. And actually understanding their star formation histories could be really helpful. It could tell us things about reionization, like how long it took reionization to occur, you know, because reionization would effectively turn off star formation. The thought is that reionization would turn off star formation rather abruptly in these galaxies.
Cool.
Because they're so small. Their gravitational potentials are tiny.
Yep.
And so if we can understand exactly when that cutoff occurs, that could actually tell us something about when reionization happened in these galaxies.
Cool.
Like if it happened at the same time in every single galaxy we look at, every single ultrafaint we look at, that tells us reionization was extremely prompt and sort of the effects happened all at once. But if we see sort of a spread, for example, that might tell us more about, you know, the duration of reionization. It might tell us about how homogeneous reionization was. If it was sort of everything everywhere all at once, or if it was, you know, some galaxies experience those effects first. So yeah, I think that would be that is a population where we don't have a lot of these spectroscopic measurements, right? So our model needs a lot of chemical abundance measurements from stars. So I know our team is trying to do that. I'm working with Evan on some work with Keck to do that.
Nice.
But I think this is something that, they're hard to measure, and the more measurements we can get, I think the more useful information we could have about this population. I think also, as I mentioned, just a better theoretical understanding of the R process at all.
Very nice, yes.
More observations of neutron star mergers, any better or updated yield sets would be, I think, really useful if we want to try to use chemical evolution modeling to tell us anything about those processes.
Nice.
Yeah.
Very cool. Very cool. And I look forward to your type 1A DDT.
Yeah. Hopefully coming out soon. Cool. To an AAS journal near you.
Open access. Go get it, people. All righty. Mia, I want to thank you so much for walking us through your awesome paper. It was really great.
Thanks so much. I had a lot of fun. I hope.
Thank you.
Hope it wasn't too much.
And that'll do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.